An emmetropic eye means that when the light rays come into the eye, the focusing mechanisms of the eye, which are primarily the cornea, the lens, very slightly, minimally, the aqueous humor and the vitreous humor, the converging mechanisms of the eye converge those light rays so that they come to a point focus on the retina. This is considered a normal 20/20 eye. It's what we all want because that point focus is very clear vision, right where that point is. Now, with a myopic eye or a hyperopic eye, these light rays that come into the eye aren't focused right on the retina in a point. For whatever reason. For the myopic eye, it might be because the eye is longer than normal. Everything else is the same. The cornea's shape is the same, the lens, everything else, but the eye itself is a little bit, maybe it's a little bit larger, maybe it's just a little bit more elongated, so that the same converging power, focusing power is there, but because the retina is moved back, the axial length is longer and the point focus comes in front of the retina, and then the light rays continue on, and what falls on the retina is not a point, it's a circle, it's a blur circle. It's bigger than a point, so it's blurry. And for hyperopia, and you could also have an axial hyperopia. These are the most common. Axial myopia and axial hyperopia. And that just means the axial length, which is the length from the cornea to the retina, is shorter or longer. In the case of myopia, we discussed longer. That's axial myopia. For hyperopia, it could be shorter than normal, and everything else the same cornea, same lens as our emmetropic eye. It's just shorter than normal. And in this case, it would be focused, well, it can't really, the light can't really be technically focused behind the retina because our anatomy precludes it. It can't get through the retina and the choroid. Light can't penetrate that. But we're just saying, if it could, it would be focused behind the retina somewhere. But what actually falls on the retina is not a fine point focus, it's a blur circle. Most eyes that are longer, that have an axial length that is longer than 24 millimeters are considered myopic. Shorter than 22 millimeters are hyperopic. That's the norm. You don't always have to have those qualifications to have myopia or hyperopia. That's not the definition. But that's probably the most common reason. You could have, well, here is what you do have to have myopia. Okay? Myopia always means too much converging power to focus light on the retina. Hyperopia always means too little converging power to focus light on the retina. So you do have to have those two conditions. It could be maybe it's because of a cornea that's too steep or too flat. And remember what happens with our steep or flat curves? The steeper the curve here, the more converging power, the shorter the focal length, the flatter the curve, the less converging power, the longer the focal length. So if we have an eye with a real steep cornea, even if everything else is the same, even if the axial length is the same as our emmetropic eye, but for some reason the cornea is steeper, maybe keratoconus or something, then you could have myopia from that. Or maybe the cornea is flatter and the axial length is the same as the emmetropic eye. You can have hyperopia from that. Okay, so I just want to stop here for one brief second because I want to go only very slightly off topic. It's still the same topic, really, but I just want you to take a look at these light rays and tell me how far away is the light source that these light rays are coming from. Okay. The light sources at optical infinity are farthest. The reason I know that is because these light rays are parallel. If I were to move the light source closer than optical infinity, the light rays would be diverging. Light rays from a source are always, always, always diverging. Be careful of that word always. Unless you have something there to change that, to converge them, such as a magnifying glass put in the way, in their path, or a lens, a convex lens. And remember, a light source doesn't necessarily mean a light bulb or a flashlight or the sun, something we tend to normally think of as a light source. A light source is anything that light's bouncing off of. So anything you're looking at is your light source. If you're looking at the person next to you, that person's your light source, because you wouldn't be able to see them unless the light was bouncing off of them into your retina. But light coming from any light source is diverging. If you look at this flashlight, you can see the casing here, let's say it's about 3 inches in diameter. But if I shine it onto a wall, is the beam of light that shows up on that wall, is it going to be a circle with 3-inch diameter? No. You already know it's going to be bigger. Why? Because the light coming out of that flashlight is diverging. Okay? Okay, so light from a light source is always diverging. Did I say always? What about when it's parallel? Well, the thing is, when you get near the light source, near the flashlight in this case, it's diverging the most. And as you travel away from the light source, it diverges less and less and less and less. And when it gets to a certain point, the divergence is so minimal, it's so minuscule that we really don't need to consider it anymore for our purposes in ophthalmic optics. And it's at that point when we just call them parallel. Technically, if you want to measure it on a real small scale, it's still diverging. But don't answer on a test that way, because we call it parallel when it gets to a certain distance, and we've chosen the distance of 20 feet or 6 meters. We call optical infinity. Okay, I wanted to mention that, and there's also one more thing that I want to kind of get clarified, because it's really important conceptually. It's a way to think of things that will make everything just a little bit easier if you consistently think of what you're doing in these terms. Okay, so let's say we have eyeglass prescriptions. One of them is a +3 spherical, and another one is a -2 spherical. What does that mean? When we see our eyeglass powers in a +3 or a -2 or plus or minus whatever, what exactly are we talking about when we say that? Well, we're talking about dioptric power, right? We know that too. Let's put it on a number line. Okay, we'll draw kind of a number line. We have a positive side and a negative side. And don't fault me, this won't be to scale. Let's see, on the positive side we have a +3. +3 means 3 units of converging power. Converging power. Plus 0.25 is going to be a lot less converging power. So +3 might look like this, whereas plus 0.25 might look like this one. So as you go towards 0 on the number line, as you back down, you're getting less and less converging power. As you go up on the number line towards 3, 4, 5, 6, you're getting more and more converging power. When you go down to 0 on our number line here of dioptric power, 0 is going to be a plano, no curve, nothing to converge. Maybe a flat lens, let's say. Doesn't have to be, but let's say it's a flat lens. Then you start going into the negative numbers. You have negative converging power. So no converging power is flat, plano. What would negative converging power be? It means less than converging power. It means less than parallel and no converging power. So when you get less than no converging power, you start diverging. So negative converging power, we sometimes call diverging, but I think it's helpful to think of it in terms of positive converging power and negative converging power. Negative converging power starts spreading apart rather than coming together. Okay, so where does that take us as far as our eyes that we drew? Okay, the myopic eye, we can see, has too much converging power. Converging power is plus power. Myopic eye has too much plus. Now, we tend to think of a myopic eye as minus because that's the prescription we give it. It's actually too much plus. And a hyperopic eye doesn't have enough plus power. And again, we tend to think of hyperopic eyes as plus because those are the prescriptions we give people with hyperopia. But we're giving them that because we need to add plus. They don't have enough. And we're giving the myopic a minus lens because we need to add minus or take away plus. You see? Okay, so again, the focal point is the point of clarity. If it falls on the retina, awesome, everything's nice and clear and crisp. The bigger the refractive error for a myope or a hyperope, the bigger the blur circle is going to be. How do we fix that? For a myope, we diverge a little bit. We take away power. Minus, subtract, take away power. For a hyperope, we add power. Okay, so here's a question. When we look at this myopic eye, what does the shape of the light actually look like? Because this is just a cross section. Say the eye was sliced in half sagittally, and you're looking at a cross section. I made it kind of triangular, but what does it actually look like? Well, it's cone shaped. In the case of this myope, it's two cones, point to point. And why is that? Because if you took this cornea off and looked at it, it would look sort of like a contact lens, right? It would be sort of a bowl shaped a little bit. And if you took rays of light coming into it, sort of like bamboo skewers as your points of light all stuck through it and stuff, it would make sort of a cone teepee looking shape. Actually, it would look like a teepee. And then, of course, those are just light rays. If you have solid light, you would have two cones. What if you had an astigmatic eye? What if you have somebody with astigmatism? Well, then you'd have that contact lens and it would be smushed a little bit. Squeeze it together a little bit, smush it a little bit. And I've drawn the astigmatisms either against the rule or with the rule to look something like this. Okay, so what happens to the light when the cornea has astigmatism like this. It's not a perfectly round, let's say. It's more oblong. And don't forget, it doesn't have to be with the rule or against the rule. It doesn't have to be 90 or 180. Those are just what we use as examples most of the time, and because statistically they're going to be 90 or 180 most of the time, but they can also be oblique angles. It doesn't matter. You can have it at any angle, but we're going to come back to this because, remember this, we're going to come back to this. I want to talk about something else first. I want to talk about what happens when the light goes through a cylinder. We talked about when the light goes through a sphere. What about a cylinder? What happens when the light goes through a cylinder? And that's the topic of the next video. So thanks for watching.